In this video, we will be talking about curved edges and sphericity. In the last video, we have talked about flat surfaces and flat bodies. In this video, we will be giving a curved edge to a body and sphericity to a body to actually match the actual shape of the particle. So how we are going to do it, we'll see it in short time. Before that, I'm going to say that in order to actually add a sphericity to the particle, we will come across this term as sphericity weightage. But just by changing this weightage, we can just give a different shape or a sphericity to the particle. If k is equal to 1, it would be like fully spherical, and this term will be actually 0. And likewise, you can change it for different values. For k is equal to 0, that's sphericity is 0 that time, and this would be fully flat with some curved edge, whatever the value of curved edge is. And the curved edge is given by a term r. We will see it how to give that one also. So, and this concept of like flat bodies, curved edges, and a sphericity is called as potential particle. You can find this thing in Yale software. I've come across this term from this, and there's research going on regarding this, and we are using potential particles. I have said that we use flat surfaces so that computation cost would be like very low, and also the space you are going to average the surface of the body, and approximation use, and the space will be also storage of the body would be also very low, and it's easy to actually comprehend. Okay, we have already talked about this flat surface. Let's get this video started now. Let's say you're going to scare this term. Will something happen? Nothing will happen. Let's say this is a body and this is top surface. So this would be like, from this one it would be like plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Here will be plus 2. Here inside would be 0. If you scare it, this will become 4. This will become just 1. So if you're scaring it, the middle one or the edge one will not change, so it won't change if you actually scare it. So I is equal to 1 and ai x plus bi y plus ci z minus z, and scaring it doesn't affect it. Okay, if you actually going to subtract a number or scare, let's say you're subtracting it like this, what will happen? So let's say that if you take, let's say r is equal to 1, let us say, so if you are gonna subtract it here, what will happen? These zeros will become minus 1, so these become negatives. This positive will become 0, so it's actually expanding. The boundary is expanding. But look at this point here, it was plus 2. From this surface it was plus 1, from this surface plus 1, it's plus 2. So this point is not actually becoming 0, not equivalent to 0 or negative. So this is greater than 0. So you can see that it's affected edge, that it's not affecting edge to get into it. It's not expanding at the edge. So the thing you might see that you will have this expanding. This was the first boundary, initial boundaries. You added r, it added up to this one, but it cannot add this corner to it. And this is the concept of curved edge. Okay, but thing is, now there's one difficulty. If you already know, here you go for normalized message, you know that d is a distance of a plane, that would put it 3. If you're going to add anything r to it, you're going to expand the boundaries. So you don't need to expand the boundaries. So that how would you compensate for that one? So you're going to put d is equal to new d dash is equal to first d minus r. So if it was 3, you're going to subtract whatever r is given, whatever the radius of corners you wanna give, not here, actually here you can give it initially, then r you can actually expand then, and it would be d, your new d dash would be equivalent to 3 then, because you're going to go d dash and it will be expanding for 3 point plus 1. It will just be, or can you see r this time, and it will be equivalent to d. So your d dash at will become d after expanding. I hope this is clear how r gives curvature at corners. Now let's give sphericity to it. So in order to give sphericity, you actually add simple the sphere function to it. What is the function of sphere? That is x square plus y square plus z square minus r square. You just have to add this thing. So the final function of the potential particle is f. We're gonna introduce 1 minus k term. What is k? K is like sphericity weightage for flat surface, like 1 minus k. I is equivalent to 1 to n number of planes. Macaulay brackets aix plus biy plus ciz minus di minus this whole square minus r square. This is roundness term, and to this we are gonna add a term, spherical term. It would be x square minus plus y square plus z square minus r square. Okay, this is in general form. In normalized form, we're going to introduce normalized form to it. Normalized, we just have to divide this by r square. So this by r square, there's the thing, how normalized works. So we will get a function 1 minus k summation of I is equal to 1 to n ai x plus bi y plus ciz minus di whole square divided by r square minus 1 plus k times x square plus y square plus z square divided by r square minus 1. So this is a normalized form, and we're going to code for this form. Okay, let's code it for it now. And this is the same code we developed in flat bodies video. We'll be continuing from this code. Let's copy this code, paste it, and just name it different particle, potential particle, and first save it up. This thing. Okay, now we need to change this gonna be same. Okay, here before this we have to write 1 minus k into f divided by r normalized square minus 1 and plus k into x square plus y square plus z square and divided by square and minus 1 okay minus 1 and close it. There are 3 new inputs. Let's write it down. One is r, one is k, and one is capital R for sphericity. Rest would be same. Let's run it and see if it's working or not. Let's name it potential particle. Let's create 3 variables. R is equal to we cannot keep it 0 because it will be like infinite here. Let's keep it something 0.01. Let's keep it as close to 0 as possible, so that we can actually mimic the last video. Flat bodies. Okay, and R you can keep it anything, it doesn't matter because k will be multiplied as 0 here, so sphericity has no meaning to it. Let's plot this flat cube first. It's saying not enough input. Okay, I haven't even mentioned it here. R k R, I think it will work. Let's wait. Okay, it's not showing because after subtracting this r, I told you in video starting of the video that it will be like less than equivalent to 0, less than 0.
So this is additional thing you need to remember. So yep, it's working very fine. This is for case counter 0. There is no sphericity in there. So if we include some sphericity in there, let's say 0.5 and a little bit of grounded radius, let's say 0.3, half of this, half of that. Let's see if it works. Yes, it's working. Spherical also, some curved edges also. Let's keep it in case 1, all sphere, no flatness to it. Let's see if it works as well. It's working very well. If you see these points, this plane point getting out, this like due to discretization. If you actually put these points close to each other, you can remove those things. So yeah, this maybe will take lots of time this time. It's saying the size is very big. That's what I said. For 3D matrix, if you actually gonna decrease the distance between 2 points, it's gonna take a lot of size. We don't need to do that. Okay, this would be it. Let's name it 0.1. Let's see how this looks like. Okay, also looking very nice. So this will be it for this video. In next video, we'll be seeing the actual application of this potential particle on the 3D soil grain. Okay, stay tuned. Thank you for watching.